I'm going to talk about moments of inertia, angular momentum, and the law of conservation of angular momentum. Let me start by drawing a picture that represents an object moving in a circle. Assume that that blue dot represents an object moving in a circle of radius r, and assume the object has a mass m, and at any instant we can calculate the velocity vector, and let's define the magnitude of the velocity vector, in other words the speed at any point in time, by the variable v. Okay? Now, you probably know that we can calculate the linear momentum by finding the product of m and v. Okay? Now let me define a new type of momentum. We can also define the angular momentum, traditionally denoted by the letter L, by finding the product of the linear momentum and r. Okay? Equivalently, we can find the product of m, v, and r. All right? So, let me repeat. The angular momentum for an object of mass m moving in a circle of radius r with a speed v is equal to the product of m, v, and r. Okay? If you have multiple objects moving in circles about the same point, you can define the total angular momentum, let's call it L subtotal, by summing up the contributions from each object. Okay? By the way, the units for angular momentum are the product of the units for mass, velocity, and radius. So the units are kilograms times meter squared, or kilogram meter squared per second. Kilogram meter squared per second, however you want to say it. Okay? So let's now immediately do an example. Suppose that a kid ties a rock to the end of a piece of string and starts twirling it in a horizontal circle. All right? Let's say that the rock has a mass of 4 kilograms. Let's say that the rock is moving in a horizontal circle with a radius of 2 meters. And let's say that it's moving with a rate of it's moving with respect to 1 revolution every second. All right? Now, we can calculate the angular momentum for the rock as follows. I'm going to find mvr. Well, the m was given, the mass was given, that's 4. The velocity, okay, that one's going to take an extra step. So the rock is moving, it's completing 1 revolution every second. 1 revolution corresponds to 1 circumference. The formula for the circumference is 2 pi r. So the speed is 2 pi times 2 meters per second. And I multiply all that by the value of r. So putting it all together, I get 32 pi kilogram meter squared per second. Okay? That's the angular momentum for this example. Now, I'd like to invite you to do an example calculation. Suppose a car is driving on a circular track. Let's say that the car has a mass of 2,000 kilograms. Let's say the car is driving with a speed of 30 meters per second. And let's say that the racetrack has a radius of 30 meters. Can you pause the video and calculate the angular momentum for this car? All right. I'll go ahead and calculate it now as well. So m, the mass is 2,000. The velocity is 30. The radius is 30. So that's equal to, let's see, 9 times 2, 18 with 5 zeros. So 1.8 million kilogram meters squared per second. I hope that's what you got. Okay, now I'd like to shift gears and revisit the equation for total angular momentum. All right? So, let me rewrite the formula for total angular momentum. So, we add the contributions from every object, and I can write the right side can equivalently be expressed by a formula that represents the product of mass, velocity, and radius for each object. Now, we also know that we can define an angular velocity for every object moving in a circle, and we can express the total angular momentum in terms of the angular velocity instead of in terms of the corresponding angular velocities for all the objects instead of the corresponding linear velocities. So if we did that, that would give us the following formula. m1 omega 1 r1 squared plus m2 omega 2 r2 squared, etc., etc. Now, if that last step was unclear, let me remind you that for an object moving in a circle, the angular velocity is the linear velocity divided by the radius of the circle. Likewise, the linear velocity is the product of the angular velocity and the radius of the circle. Okay, so what I did was I substituted omega r, the corresponding product of angular velocity and radius for each object. Okay, now let's think about what is special about, or how would this equation change if we weren't talking about separate objects, but all the pieces of a rigid body. So in other words, think about a top spinning, a bat swinging, a door opening or closing. Okay, so for those examples, what we have to do to find the total angular momentum of the rotating object is add the contributions from all the pieces of the rigid object, right? Okay, so the equation is the same. There is one simplification we could make. Notice that all the parts of a rigid body that are rotating have the same angular velocity. Let me repeat that. For a rigid body that is rotating about an axis of rotation, all the parts have the same angular velocity. So what that means is that I can factor out the omega 1, the omega 2, omega 3, etc., etc. Those are all the same value. So I'm going to write the total angular momentum for a rotating rigid body with this simpler version. Okay, now this comes up so much, okay, that we give a special name for the blue expression in parentheses. We call that the moment of inertia for a rigid body, okay? And that traditionally is denoted by the variable I. So let me write what I just said, then an equation and definition that corresponds to what I just said. So the moment of inertia, I, of a rigid body is equal to the sum of is equal to this sum, where each of the M1, M2, that corresponds to the contributions from all the little pieces of the rigid body. All right? Furthermore, notice that the total angular momentum for a rigid body has this alternative, simpler formula. The total angular momentum for a rigid body undergoing rotation is equal to the product of its moment of inertia and the angular velocity with respect to that rotation. Okay? Now, calculating the moment of inertia for a rigid body, for common shapes like solid spheres, solid cylinders, baseball bats, okay, that is a tedious process that typically involves calculus. Okay? I'm not going to derive the moments of inertia of various shaped objects. Instead, what I'm going to do is I'm simply going to list the moments of inertia of common situations. Okay? I would encourage you to Google for tables of a table of moments of inertia. If you do that, you will see all kinds of wonderful formulas for cylinders, spheres, etc., etc. Okay? And you can, if you do that, you will see that some of those formulas are what I'm going to give you right now. So the moment of inertia for a solid sphere with an axis of rotation through the center. Okay, so let me maybe draw a corresponding picture. Suppose I had, let's say, like a like a bowling ball that was spinning with an axis of rotation through its center. Okay, let's furthermore say that the bowling ball has a mass m. Let's make it a lowercase m. And let's say that the sphere has a radius r. Let's make it capital R to distinguish from the a general R for a polar coordinate variable. Okay, so for this solid sphere with a mass m and a radius r, the total moment of inertia, the moment of inertia for this situation is 2/5 mr squared. Okay, that's what you will get if you were to add up the mr squareds for all the little pieces. Okay, now what does it mean to add up all the mr squares for all the little pieces? So what is that little r? What is the meaning of the little r in the moment of inertia equation? Well, what you'd have to do is for every little piece of the bowling ball, let me put a little square to denote a small piece, okay? And you would have to multiply the mass of that little piece by its distance from the axis of rotation. Okay, so can you see that all the little pieces of the bowling ball will have a different distance? All different pieces will have varying distances from the axis of rotation. All right, so that's one example of a moment of inertia formula. All right, let me give you another one. So suppose we wanted to know the moment of inertia for a cylinder that was undergoing rotation with respect to an axis through its center. So let me draw a cylinder. Let me draw a line to represent an axis of rotation through its center. And once again, let's say that this object has a mass let's say it has a mass m, and let's say that the corresponding radius of the cylinder is capital R. So let me draw a line that shows you what I'm talking about. And so the length of that line segment is capital R. Okay, so for that example, the moment of inertia, so this is a solid cylinder with an axis of rotation through the center, so I'll write center in parentheses. Okay, so that's equal to 1/2 mr squared. Okay, now once again, if it's not clear where this formula came from, to find the formula for a cylinder, you would have to add up the mass of all the little pieces that make up the cylinder and their corresponding distances from the axis of rotation. So if you know what an integral is from calculus, you would likely need an integral to calculate it for the object that you're interested in. Okay, but I'll give you the answer that you would get if you did it the hard way. Okay, so please write these down, and we will do some examples involving them. And then, as I said, you can do an internet search for a table of moments of inertia, and you will see lots of formulas such as these two. All right, so let me do an example, and then I'll have you do one. So let's assume that a bowling ball has a mass of 30 kilograms. Let's assume that it's spinning with respect to an axis of rotation through its center. Maybe somebody started a bowling ball spinning on a table. Okay, and let's assume it's spinning with respect to 0.5 revolutions per second. And let's assume that the bowling ball has a radius of 0.2 meters. Watch me calculate the angular momentum for the bowling ball. All right, so the bowling ball is a solid sphere. And so the formula for the moment of inertia of the bowling ball is 2/5 mr squared. The formula for the angular momentum, L, is I times the corresponding angular velocity. And so now let's put it all together and see what we get. So 2/5 times m was 30 times r squared, so 0.2 squared. The angular velocity, let's see, 1/2 revolution per second, that's pi radians per second, right? All right, and let's see if we could simplify this. So 2 times 30 divided by 5, that's 60 divided by 5, that's 12. 0.2 squared, that's 0.04. 0.04, 4% of 12 is something with a 4 and an 8. 10% is 1.2, so 0.48 is that part multiplied by pi. So 0.48 pi kilogram meter squared per second, and you can get a decimal for that with your calculator if you wish. Okay? Now, let me have you do one. So, have you ever seen a potter with his or her spinning wheel? Now, I don't know much about making pottery, but I've seen there's a spinning surface, and they put a mound of clay, and then they start getting their hands dirty, and out of that whole process comes some wonderful looking pottery. So let's assume that a potter just put a mound of clay on one of those spinning contraptions, and let's say that the amount of clay is initially in the shape of a cylinder. Okay, so let's say that there's 20 kilograms worth of clay, and let's say that the radius of that cylinder is 0.1 meters, and let's say that the spinning cylinder of clay is spinning with respect to 2 revolutions per second. All right, so pause the video and see if you can calculate the corresponding angular momentum for this solid cylinder undergoing rotation. Do that now, please. All right, I will go ahead and calculate it also. So the formula for the moment of inertia of a solid cylinder is 1/2 m times the square of the radius. The formula for the angular momentum, L, is I times the corresponding angular velocity, which I'll denote by omega. So let's see what that gives us. So 1/2 times m is 20 times r squared, so 0.1 squared. And then for omega, 2 revolutions per second. Each revolution corresponds to 2 pi radians, so that's 4 pi radians per second. And so now let's see if we can simplify that. So 10 times 10 to the minus 1 squared times 4 pi, 10 times 10 to the minus 2 times 4 pi, 10 to the minus 1 times 4, so 0.4 pi kilogram meters squared per second. I hope that is what you got. Okay, so I've defined angular momentum in this video. I've defined total angular momentum. I've defined moment of inertia. Now, let me make one other comment about angular momentum that we will see more of. Okay, so let me clear the board first. Okay, one reason that angular momentum is a useful definition is because in lots of situations it is constant. Okay, when is the angular momentum of a system constant? When the net torque is 0. Okay, let me spell this out now. This is referred to as the law of conservation of angular momentum. Okay, if the net torque on a system is 0 Newton meters, then the total angular momentum of the system is conserved. So in other words, that product of I and omega, okay, for a rigid body is going to be constant. If it's not a rigid body, then the sum of all the MVRs, the corresponding mass velocity radius products, are going to be constant. Okay. Now, I'll make one observation that you might find amusing. You might know that if an ice skater or a dancer goes into a spin, you may have seen that on TV or maybe in real life, you might know that if they pull their arms in, it actually increases their angular velocity. Okay? That can be understood in terms of the law of conservation of angular momentum. Let me show you how. So let me write the formula for the angular momentum of a rigid body. Okay? And remember that the moment of inertia, that variable I, is the sum of all those mass times radius squared contributions, okay? Where the radius, or the r, little r variable, corresponds to the distance from the axis of rotation. So as a ice skater or a dancer brings his or her arms in, can you see that that will decrease the moment of inertia? Okay, why is that? Because we're decreasing the distance of some of the mass from the axis of rotation. Okay, so the long and short of it is that the I variable value is going to get smaller. But wait a minute, we just said that the L value has to stay constant. Okay, so let me say it as simply as I can. The I variable is getting smaller, but the L variable value can't change. What does that mean? How can we accomplish that? Well, the only way is if the omega increases. Okay, if I get smaller, omega has to get bigger in just the right amount so that the product of I and omega stays constant. That is one way to explain why a dancer or ice skater moving his or her arms into her body, closer to her body, increases the angular velocity. Okay, I thought that was kind of interesting.